Section 1.5 and 1.6 combined. We're going to put these notes all together since they're going to be on the same day. So 1.5 combinations of functions, the first thing that I've highlighted there, so these are going to be the notes for that first section. All right, so basically all we're going to be doing in this section is just adding, subtracting, multiplying, and dividing the different functions. So first notation, we have f plus or minus g of x. So we're going to put this into two parts. We're going to do the plus part and then the minus part separately. So I'm going to label these as A, B, C, and D just in the order that we're going to be doing them. So I figure we'll do f plus g of x first. And it really is as simple as it looks. Take the two functions, add them together. So for my f of x, I'm going to have 3x minus 1. And I am going to be showing more work here than is necessary. We're perfectly fine if you just go ahead and combine like terms from the get-go. So if I add these two together, it looks like I'm going to get 5x and plus 4. So there's the f plus g of x. And then moving on to the second one, so embedded into that very first part, the f plus or minus g of x, let's do the subtraction. And it really is as simple as you think it's going to be. Just take the f function and subtract the g function. Combine like terms, looks like we're going to get an x when we subtract and a negative 6. Alright, part C. Now we're on to the multiplication part. So we have fg of x. Alright, I'm just going to take the two functions and multiply them together. So take my 3x minus 1 times my 2x plus 5 and multiply that out. So if you're a box person, use your boxes. If you're not, go ahead and just multiply it out yourself. So we're going to get a 6x squared. Looks like I get a 15 and a minus 2, so plus 13x, and then a negative 5. So I went ahead and just combined like terms. I'm not a box person, so I go ahead and just do the multiplication in my head. And then D is just going to be the division of the two. The only thing you need to keep in mind here, just like the subtraction one, is that for the subtraction you need to pay attention to who's first, so that function comes first when you subtract. And then in division you need to make sure that the f function actually goes on top and the g function goes on the bottom. So I get 3x minus 1 all over 2x plus 5. There's nothing you can actually do here since neither one of those are factorable. That's the best you can do. So just some basic operations with two functions that were given to us. So now we're just going to use the two previous functions to be able to determine what fog and goff are. So this is when we compose the two functions together. So if we do fog of x first, remember the order, oh, that's a little big. The order in which you actually plug these into each other is kind of backwards. So you're going to start with the g of x here, and you're going to plug that in to the f. So take my f function, so just start merrily writing your f function, and then as soon as you run into an x, pull it out and plug in the g function. Don't forget that minus 1 at the end as well, and then just go ahead and distribute and combine like terms. So it's going to give me a 6x when I multiply. It looks like a 15 minus 1 is going to be 14. You don't have to factor this or do anything else with it. That's it for fog. Goff, basically the same thing, except now you're going to start with the f function and you're going to plug it into the g. So this one goes in there. So do the same thing. Merrily start right in the g function, and then whenever you run into an x, rip it out and put in the f function. And then don't forget that plus 5 at the end. Distribute. It's going to give me a 6x. Gives me a minus 2 plus 5, so plus 3. Alright, so fog and goff. Now on to section 1.6 of the notes. This is about inverse functions. This is where we're really going to be talking about how doing the composition of fog and goff, making sure that they equal x, will determine that the two functions are actually inverses of each other. So that's what we're going to work on here. One of the things, and I know this is something that you've worked on previously last year, One of the things here is it's extremely imperative that you show all of your steps and make sure that you clearly label what you're doing. So the first one I'm going to do is fog. Alright, so that means, again, previously, I'm going to start writing my f function. Every time I run into an x, I'm going to pull it out and I'm going to plug in the g function. So my f function starts at 2, there's the x, take it out. And inside that, you're going to replace it with the g function. After you've reached the end of the x, I like closing or putting parentheses or brackets or something around it, just so I can see that I've actually plugged something in. And then don't forget to write the rest of the f function itself. Okay, so there's fog. Now we have to obey order of operations and just do the math. So based off of this, it looks to me like we're going to have to get rid of the cube and the cube root first. So if I eliminate those two, these go away. I'm going to get 2 times, now the radical's completely gone, since that root belonged with the 3 that we just canceled out. Now, there are a couple ways that you could do this. You can go ahead and distribute the 2 to the top if you want to, but I'm not going to. I just see that the 2's cancel here. So now I can drop the parentheses because nothing's going to be multiplied to the x plus 1. And now my 1's disappear. So I get an x. This is good. So I'm trying to prove that fog and goff are inverses of each other. If I tell you prove or verify, it works, I promise. You just need to make sure that you show me through all of your steps that you actually do get that fog and goff are both equal to x. Alright, so let's do goff. I'm going to do the exact same thing, except now I'm going to start writing the g function, and then as soon as I run into the x, right there, I'm going to pull it out and I'm going to replace it with f. Then continue writing the rest of your function. Okay, so now obeying order of operations is really your friend here. If I take a look at this, I can't get rid of the cube and the cube root yet because I have stuff going on inside. I can't get rid of the 2's because that 2 in the denominator is dividing into everything on the top. So yes, you can divide the 2 if you want to, but I think I'm going after the 1's first. So those are going to go away. Now I'm going to copy down what I wrote. Make sure that you don't skip any steps like I said. If you do, I'm unaware what step you did first, second, third, so on and so forth, and I'm not sure if you obeyed order of operations. So again, make sure that you show all of your steps. 2's get to go this time. And then the last thing that's going to go is the cube and the cube root. And there I have x. Now, when we take a look at this, we have that fog equals x and we have goff equals x. So now I just need to make a statement at the end. So therefore, and there's just a couple ways you can do this. You can say it in whatever words you want as long as you're saying the same thing. Therefore, fog of x equals goff of x equals x. So I'm basically saying that both of those things are both equal to x and they happen to be equal to each other. Because of that, this implies the original functions f of x and g of x are inverse functions. So the steps that I need to cover, going back up to the beginning. You need to plug in fog. Make sure that you show all of your steps. I would highly recommend some sort of parentheses or brackets or enclosure, something so you can see that you've actually plugged it in thoroughly. Then don't skip steps. Obey order of operations, show everything. Do the same thing for goff. Then at the very end, make sure that you include some sort of a statement. So I showed that fog is equal to x and goff of equal to x. I now know that f of x and g of x are inverse functions. So you're kind of looking at a whole bunch of stuff here. The key thing is, though, watch your steps. That's really important. Okay, same idea here on number 2. We're going to, so previously I said on the prior slide, prove that they're inverse functions. Now I'm saying verify algebraically. It's the same thing. So the only reason why I chose to use these two different wordings is because on tests or quizzes or whatever, we will go through sometimes and use different vocabulary to identify what we're looking for, but they all mean the same thing. So again, this is verify algebraically, which means it works. So keep that in mind. All right, fog of x. Remember, you start writing the f function, and every time you run into an x, you rip it out and you plug in the g. Okay, so the f function starts out with a 3, there's an x, take it out. Go to the g function and plug that in. Notice I'm using parentheses when I plug my g function in. And so it's 3x plus 4, still continuing on with my f function, over, still looking at my f function, and there's another x. Pull it out. So now I have fog all plugged in. I think I'm going to do what I've done on some previous slides for notes. I'm going to kill the denominators. I don't particularly like them being there, so I think it looks ugly. So the common denominator on the top, let's go ahead and give everybody a denominator that doesn't have one. The common denominator on the top is going to be 5x plus 3 and 5x plus 3 on the bottom. So let's just go ahead and multiply by that. So 5x plus 3 on top and 5x plus 3 on the bottom. And now all we're going to do is distribute. So if I distribute my 5x plus 3 to the first thing, which is this guy right here. So if I distribute there, I see that the 5x plus 3 numerator and the 5x plus 3 denominator are going to cancel. So all I'm going to have left from that, and I'm just going to keep with the red, is I have the 3 out in front still, and just the numerator of the fraction, 6x minus 4. Then, let's move on to the next one. I'm going to do the same thing here. So my next term is this 4. If I distribute by 5x plus 3 to my 4, I'm just going to get a 4 times 5x plus 3. All over. I'm going to do the exact same thing on the bottom. So let's go ahead and distribute the bottom there. Let's use purple this time. So this is the one I'm going to be distributing to next. And I'm going to get, there's nothing to cancel, so I'm going to get a 6 and the 5x plus 3. And then that next term, right here, is going to cancel out the 5x plus 3's this time. So it looks like I have a subtract, so a minus 5 times, and then the only thing that's left is the numerator from that fraction. Okay, so we have successfully killed the denominator. Now, hopefully I didn't make any algebra mistakes. Now I'm going to distribute the top and distribute the bottom. So if I do that, I'm going to get 18x minus 12 plus 20x plus 12 all over 30x plus 18 minus 30x plus 20. All right, looking good so far. Now there's a couple things that I can do here at once because the numerator and the denominator don't affect each other until I start doing division. So if I see like terms that I can combine, I can actually do that. So I see my 12s are going to go away, and it looks like I'm going to get a 38x on the top. Now, I combined those steps together because it doesn't matter which one you do first. I am under the impression that you aren't going to cancel the 12s with an 18 or a 12 with a 20 because they aren't like terms. So we can do the same thing on the bottom. My 30x's cancel, and now I can combine the 18 and the 20. This is good. There's the 38, those cancel, I get an x. Okay, so fog, we are successful. Let's do Goff. Same idea. Start with my g function. Everywhere I see an x, rip it out and plug the f in. So, my g function, there's the x. take it out, plug in f. Minus 4 all over. Okay, still on my g function. 5, c and x, rip it out, plug in the f function. And then back to my g function. Alright, so I think I'm plugged in successfully. Now I'm going to do the exact same thing. I'm just going to kill the denominators. So this is one way that you can do it. If you have other ideas of how to do it, that's fine. Just talk to your teacher and make sure that those are valid methods. This is the method that I choose, just because I don't like getting common denominators if I don't have to. I'm kind of using the common denominator here. I'm just using it to annihilate the fractions, though. Okay, I'm not going to color code this one, but I am going to go ahead and just distribute. So same idea here. Oh, let's give everybody a denominator. Sorry about that. If I distribute my 6 minus 5x to the very first part, denominators cancel. All I have left is the 6 out in front and that 3x plus 4 from the top of the fraction. Then, if I distribute my 6 minus 5x to the next one, that minus 4, well, there is no fraction denominator at all that's going to cancel. It's just a 1. So I just bring my 6 minus 5x times my negative 4 that was there. Okay, same thing. Take my 6 minus 5x, multiply it to the first one. Those denominators are going to cancel. So now I just get the 5 that was already there and the 3x plus 4 from the top of the fraction. Plus, distribute it to my second one, 3. There is no denominator other than the 1, so they don't cancel. Okay. Now, let's go ahead and distribute. So hopefully I didn't make any algebra mistakes here. I think I paused the recording in the middle of that statement. My apologies. So this is going to be 18x plus 24 minus 24. Okay, this is good. I see my 24s are going to cancel. Plus 20x all over. Distribute 15x plus 20 plus 18 minus 15x. Alright, hopefully everything goes away like it's supposed to. Alright, let's take a look at this. 24s go away on the top, an 18 and a 20 give me a 38x. And then my 15x's go away on the bottom, and I get a 38 on the bottom. Okay, good. This worked out. And remember, the directions said verify algebraically. So I'm telling you it works. We just need to make sure that we don't lose ourselves in the mess here somewhere. All right, so then my final statement. So I can say fog of x equals gof of x. Just saying that all three of them, that both of those, gof and fog, equal the same thing. This implies f of x and g of x are inverse functions. Okay. So a little bit of practice with fog and gof and doing inverses. Okay, so what we want to do now is determine if the functions are one-to-one. It basically means that the original function without any type of restriction its inverse is going to be a function as well. So in order to do that, we use dummy variables. The common ones that we use are a and b, but you can use anything that you want. You don't want to use x and y just because that would be a little confusing. So all we're going to do is we're going to determine what f of a is and f of b is. So let's just plug in some a's and b's. So for f of a, I'm going to get a squared. For f of b, I'm going to get b squared. Alright, so now here's what we want to do. We want to determine if these two are actually going to be equal to each other. So I'm going to take my f of a, which is a squared, and I'm going to set it equal to my f of b, which is b squared. And I'm going to ask myself if that has to be true. All right, well, I think that I just want to get a and b to be able to do this. So I think I'm going to have to square root both sides. So let's square root a squared. Still not sure if these are equal. Keep my question mark there, and square root b squared. But I forgot something. Every time I square root, if it wasn't there originally, I have to put in plus or minus, because there's technically 2 square roots to everything, except for 0. That's the special case. So now, with my plus or minuses in, I can go ahead and square root these guys. So square root of a squared is going to be plus or minus a, and the square root, still checking, square root of b squared is going to be plus or minus b. So the question is, does a equal b? Well, you have to ask yourself if it's guaranteed. Is it guaranteed that a is going to be equal to b in this situation? And the answer is no, absolutely not. So this is not guaranteed. And I'll show you why. Because of those nasty little pluses and minuses, I know that, well, let's say I've got the positive a, that could be equal to the positive b. This is what I want. This makes me happy. However, because of that plus or minus, maybe positive a is equal to negative b. This is not what I want. That's bad. But I have all these options. Maybe negative a is equal to positive b. Don't want that one either. Maybe negative a is equal to negative b. Don't want that one either. Because you have options, because a and b have that plus or minus business going on, there's a possibility that a doesn't have to be equal to b. It could be equal to the negative aspect of it. Because of all of these options, the original function is not one-to-one. It is because of all of these options, all of these bad little guys that I put the little mark next to. So that's a no. Let's take a look at the next one though. So I'm going to do g of a. And g of b. Then I want to determine if a and b have to be equal to each other. Or actually, they are. So not sure. Well, let's manipulate. So, I think I would probably get rid of my 9s first. So let's get rid of those. And divide by 3. Notice, because all I did was divide and do some addition and subtraction, I didn't have to put in any type of like a square root or a square or plus or minus or anything else like that. So is it guaranteed that a is equal to b? Yes, absolutely. Because there were no random little plus or minuses, there's no 2 we couldn't get rid of, there was nothing that we couldn't eliminate to just get the a and the b by itself. So it is guaranteed that a is equal to b. So I can say my original function, which I called g of x, is 1-to-1. So to determine 1-to-oneness, we basically just plug in some dummy variables, an a and a b, or a c and a d, a smiley face and a question mark, whatever you want to do, and then just determine if those two things absolutely have to be guaranteed to be equal to each other. If they do, it's 1-to-1. If not, it's not. Okay, so I'm going to restrict the domain to guarantee that the inverse is a function and identify the inverse function. So we just have a basic parabola here. So I think what I'm going to do is I'm just going to take a minute and I'm going to go and graph this thing. Okay, so I've got my visual here of my parabola that's going to have a vertex at 9, 1. So I'm going to just get a quick sketch of it. And what I want to do is I want to determine where this thing starts failing the horizontal line test? And what is that point where I can kind of chop the graph off? So what I look for whenever I'm looking for a parabola and trying to restrict the domain, I always look for the vertex, because the vertex is that point at which you start getting that symmetry happening. So every point on the left is going to have a partner on the right, and so on and so forth. So what I'm going to do is I'm going to just take a line here and identify where the vertex is located. What that tells me is that everything past this line, so if I started at the very bottom, it doesn't look like it's that big of a deal, but I'm not really hitting the graph, so it really is a big deal. Horizontal line test. I'm not hitting the graph at all, so it's not doing anything for me yet. Horizontal line test. Still not hitting the graph. All right. Whoa, that's not what I want. See if this obeys. There we go. Another horizontal line test. I'm looking good so far. I'm now hitting the parabola. But as soon as I go past the vertex, I'm in trouble. I've now failed the horizontal line test. So horizontal line test is going to help me figure out where I should start chopping stuff off. So let's get rid of that horizontal line that we just put in. And what we want to do is I want to restrict it. Now I like having the right hand side of my graph personally. It doesn't really matter which way you go with this. So I think what I want to do is I want to start chopping it off. So let's keep the right and let's chop off the left here. So let's get rid of those guys. So now what I'm going to do is I'm going to restrict the domain at the vertex. So for every parabola, I'm going to restrict at the vertex. And in this case, the vertex was at 9, 1. Now, we need to figure out how we're supposed to restrict that with regard to the inverse itself. So let's start working on the inverse function. Okay, so to start working on the inverse of the function, go back to stuff that you did last year. So not necessarily something that we work on a huge amount this year, but it is some knowledge that you're going to need. So the whole idea of starting with a function and finding its inverse by doing the whole swap and solve type method. So what I'm going to do is I'm going to take my k of x, I'm going to replace it with a y, so I can do that whole swapping part, and then just write down the rest of the function. So now the swapping. Every x becomes a y, and every y becomes an x. Now we solve. Minus the 1. And then we're going to need to square root. Now, I don't want to put the plus or minus in, because if I do that, I get both pieces of the parabola flipped, and I don't want that. I only want the right side, and because I want the right side, I'm only going to do the positive square root. Now, if you chose the left side, you would do negative square root x minus 1. I chose the right. Doesn't matter which way you go. Most books tend to use the right-hand side, or the positive aspect of it. Add my 9. And then the last thing I need to do, this is a function. I've already guaranteed this by not putting the plus or minus in front of it. And I'm going to rename it as k inverse. So there's my inverse function of the restricted part. Now I have to rename or rewrite k with its restriction. Alright, so I take my k of x function, original one I started with, and I chose to go to the right hand side, so I need my x to be greater than or equal to the x value of the vertex, which is 9. So that's where I chopped it off. That's going to include my restriction. So this last little part is really important, because this tells you what portion of the graph you're keeping and what portion you're going to be throwing away. Last question for the notes, coming back to piecewise functions that we did a couple of sections ago. Now what we want to do is we want to insert another piece to create a continuous function. Continuous means that if we put our pencil on the paper, we should be able to trace the entire graph without lifting your pencil off the paper at all. So any holes are going to need to be filled in, any jumps are going to have to be taken care of. So we need to make sure that this thing is absolutely 100% continuous. So I think what I'm going to do, I'm going to pause and I'm going to graph this piecewise function. This would be an excellent time for you to pause and see if you can graph it as well. Remember, we did this a couple sections back, so this is a good little test for yourself. Okay, so hopefully you did well and your graph looks the same as mine. So this is clearly not a continuous function because we have this big huge gap in between the orange and the blue. So my job is to find something that goes between the orange and the blue. Back in my table that I used for coming up with the points to be able to graph these two different pieces of the function f of x, I need to take a look at what are the 2 points that I should be able to connect to be able to get this nice continuous graph. It doesn't have to be smooth. It's going to be kind of, sharp in some corners, but I need it to be continuous. So what I need to do is I need to fill in the gap. What I'd like to do, and I'm just going to go ahead and put it in right now, I'm going to use green. I would like to have a hole around the orange thing. This orange point here. And I would like to fill in the blue to get it continuous. And then the easiest way to connect these 2 points is a line. So what I want to do is I want to find the equation of that line. So let's do that. So I need to know that first orange point is going to belong to my green line as well. And based off of the graph, it looks like that this is at 1, 2. So I'm going to need that point. And then the blue point where that one starts looks like it's going to be at 4, 3. And I'm going to need that point as well. Okay, so now we're basically back to the very first section that we did, which was writing the equation of a line. So if I take those 2 points now, so my 1, 2 and my 4, 3, and I want to create the equation of a line between those 2 points. Well, I need slope. So my slope is going to be my rise over my run, which looks like it's going to be 1/3, which I could have done just by looking at the graph and counting. See, it's up 1, right 3. Now, the next thing that I know, or I need, is one of the points, just one of them. It doesn't matter which one you pick, just pick the one that makes you happier. I think I'm going to pick the first one just because it looks easier. So, and I'll plug it into my y minus y1 is equal to mx minus x1. Okay, now, this is the equation of the line, but I need to include the restriction, and I need to get this thing equal to y, because y is the name of f of x, or g of x. So I need y equals. I'm not going to distribute, that's extra work. I'm just going to add the 1 to the end. So I'll move this over. Okay, so now there's my function. Now I need my restriction. Taking a look back at my graph, I wanted to have an open circle at x equals 1. So I want an open circle at x equals 1. And I wanted a closed, filled in circle at x equals 4. Alright, so I know that the 1 is going to be on the left, the x is going to be in the middle, and the 4 is going to be on the right. I want it to be open on the 1, so no equal to, and I want it to be closed on the 4. Definitely equal to. Now, all I need to do is just write my g of x function now. So my entire g of x function is going to include all of the parts. So g of x, all right. Now I'm going to have 3 pieces. So the first piece was the one I started with, 3 minus x squared, where x was less than or equal to 1. The one at the end, I also had 2x minus 5, x greater than 4. Now, the one in the middle is the one I just came up with, so I'm going to fill that one in. So 1/3 x minus 2 plus 1, and my restriction, there we go. We have a full, complete, continuous function that is now going to be called g of x, because f of x was just the orange and the blue. G of x is the continuous that includes all of them. So you need to make sure at the very end that you do have the entire g of x function that includes all 3 of them.